Hello, welcome back. I just wanted to go over some astronomy challenges in the classroom that hopefully you guys can find useful and take advantage of some hints and things like that. So we're going to be solving flux problems. As you remember in our class, we learned that flux, the brightness, apparent brightness in a given planet is basically a function of the luminosity of the star, like our sun, for example, divided by the surface area and the distance from that given source. So it's luminosity divided by 4 pi times the distance squared. Normally the distance is in meters. So how do we figure to do this challenge? Before we get into the details of it, I just want to kind of reminder of a couple of things in terms of the rules of exponents on base 10. So a couple of the rules in arithmetic that we want to kind of review, simple stuff. If you take 10, for example, squared, which is 100, and you multiply it by any base 10, say for example to the third power, the multiplication implies that you add the exponents. If you remember your algebra, this would equal to 10 to the fifth power. And that applies, and that's something that you can use all the time. For example, if you have 10 to the 11th power times 10 to the 5th times 10 to the 6th power, well, that would equal the addition of 11 plus 5 is 16 plus 6 is 22. So that would be 10 to the 22nd power. So it's as simple as that to be able to multiply. And we want you to, in astronomy, because we're dealing with such huge quantities, either in terms of power or in terms of distance, to remain within the power of 10. The division is likewise just as easy. For example, if you have 10 to the fifth power divided by 10 to the third, the rule says that you subtract then the exponents as you figure out the division. So it would be 10, 5 minus 3 is 2, that would be 10 squared. You can verify by multiplying 10 times 10 times 10 5 times, and then 10 times 10 times 10 3 times, and cancel out the zeros, and you'll find out that you get 100, 10 squared. But you don't want to do that. You want to maintain the power of 10 and the exponents like this. That way it's easier to work. Another example, 10 to the 26 divided by 10 to the 11th power. All you do is subtract 26 minus 11. That would be 10 to the 15th power. Boom, simple. Okay, so just remember the rules of 10, and then that will allow us to solve any problem that we deal in flux, at least, keeping it simpler for you to do the arithmetic. So in this case, let's figure out the flux on the Earth. What is the apparent brightness on the Earth from our given star, the sun? So there's a couple of givens. Luminosity is equal to 3.9, that's the power of the source, times 10 to the 26 watts. It's a huge number. The power of the sun is unbelievable. That's a huge number. So if you take the luminosity of that number of watts, the distance in AUs is 1 AU, which is equal to 150 million kilometers, or 1.5 times 10 to the 11 meters. Okay, so we have that right there in terms of distance, and then we have, of course, the luminosity. We know for sure that the brightness of a given object is inversely proportional to the distance. So we have those two. All we have to do is replace that formula and then solve the problem. This is where the arithmetic comes in and frustrates some kids. So let's go through this kind of straightforward. So the flux is equal to 3.9 times 10 to the 26 watts divided by 4 pi times 1.5 times 10 to the 11 meters, the whole thing squared. So that's pretty easy. That's easy to resolve. Now all we need to do is we're going to keep the 10 to the 11 and square it, 1.5 and square it, and solve the denominator. So let me do that slowly. We're going to keep the numerator exactly the same. So Even though it seems repetitive, let's try doing that. 3.9 times 10 to the 26 watts divided by 4 times, now I'm going to convert a pi into a number, which is 3.14. You can use your calculators that have a more precise number, but pi at 3.14 for our purposes will work. Now times, I'm going to go ahead and 1.5 times 1.5, I'm squaring that number, is 2.25. That you can find out by multiplying it on the side or with your calculator, figuring out what 1.5 squared is. I'm just taking it slowly. Times 10 to the 11th squared would be 10 to the 22nd, and then meter squared is implicit as we squared m. Okay. Now, once I do that, I can go ahead and simply multiply the denominator first. So I'm going to copy the numerator and leave it alone, and times 10 to the 26. Math needs to be kept pretty neat, so you don't have to mess with that. So if I multiply 4 times 3.14 times 2.15, the result is 28.26. Okay. Now I'm going to leave the rest the same. So I multiply 4 times 3.14 times 2.25 times 10 to the 22nd meters squared. Now all I need to do is do the division of this number and this number, and then we'll take care of the exponents on 10. So that would be F is equal to, the flux would be equal to basically 3.9 divided by 28.26 is 0.1380. Now times 10, 26 minus 22 would be 10 to the 4th, and we keep our units, watt per meter squared. Now 1380 times 4, now we can get rid of the exponent. We go 1, 2, 3, 4. So the flux is equal to 1380 watts per square meter for the Earth. That's our answer. It's just as simple as that. Not a very big deal. Nice and clean and neat. There's not much you need to do about that. By the way, this is called, again, the solar constant. Now, one of the things that you can do to be able to earn extra credit is to just simply be able to do that for Jupiter. It's 5.2 AUs from the Sun, and say Venus at 0.723 AUs. Now, to earn that extra credit, all you need to do is basically work out the problems very similar to this with full understanding, and then show your teacher, and you will earn extra credit. Good luck. Thanks.